Okay, so we're going to practice solving optimization problems. It's good to have an outline to follow, and so these are my version of the steps that are proposed in your textbook. Let's start by reading and then filling in two words. Okay, first word is going to be either maximize or minimize, and the second word is what it is we want to maximize or minimize. What do we want to optimize? Okay, in this problem it's pretty easy to pick out, because we can see right here, find the maximum area. So step one, we want to maximize area. Right. This is actually kind of important. Right. Area is what we're trying to maximize, and we're going to need to find a function that describes our area. Step two, draw a picture, get some notation in there. All right. So we're trying to find a rectangle that's inscribed between the graph of this function. This function might be easier to look at if we write it as 3 minus x to the fourth. X to the fourth is a little bit like a parabola with its vertex at the origin. The minus sign says we're going to flip it over and raise it 3. So our picture is something like this. We're going to have a y-intercept at 3. This picture is far from perfect, but it doesn't need to be perfect. Right? It just needs to suffice to help us make a cartoon. It would be useful to know where these x-intercepts are. If I set this equal to 0, it's not too hard to solve that this is the fourth root of 3 to the 3 and negative fourth root of 3. And we want to fit a rectangle in there between the x-axis and the curve. So that rectangle is going to look something like this. And the thing that we can change or move around in this picture is essentially this point right here. Right? If we move the point on the graph, then the rectangle changes. For instance, if I move the point down to here, I'd have a longer or wider, shorter rectangle. If I move the point up to say here, I'd have a taller, narrow rectangle. Okay. The one with maximum volume is clearly going to be somewhere between this short, wide one and this tall, narrow one. Something like what we have in black there. But what exactly is the ideal location? Right. So if this is the point on the x-axis with x-coordinate x, then my rectangle here has width 2x and it has height y. All right. Step 3. Write the quantity that we want to optimize. We'll call it Q. In this case, we'll call it A for area in terms of the variables. Well, our area is the width of the rectangle, 2x, times the height of the rectangle, y. All right. If you've got more than one variable in there, you're going to need to reduce it to one variable. How can I do that? Well, I know here that y, the y-coordinate on the graph, is equal to 3 minus x to the fourth. This point here that we can move around has coordinates x, and then 3 minus x to the fourth. So y is 3 minus x to the fourth. So I can use that in my equation. All right. To get this in a more calc-friendly form, I might multiply it out. So I get 6x minus 2x to the fifth. What are the limits on x? All right, what is the domain of this quantity we want to optimize? Well, it's pretty clear that I need x to be greater than or equal to 0. And I can't push x over here, past here, because then my rectangle doesn't make sense. So I need x to be less than or equal to 3 to the 1/4. Right. So x is in the closed interval from 0 to 3, the fourth root of 3. Right. I find this step to be very important. All right. Now I know that I have a continuous function on a closed interval. And if I do have a continuous function on a closed interval, it has an absolute max and an absolute min. And I can use the closed interval method to find it. So now we're going to find the absolute max and min using calculus. So this is really the only step in the whole thing that takes calculus. Everything is modeling and algebra. We have a calculus step, and then at the end we're going to just make certain we've actually answered the question. So the closed interval method, a reminder, says if we have a continuous function on a closed interval, the way to find the absolute max and the absolute min is to make a list, right, that includes the endpoints of the interval and then any critical numbers that lie inside that interval. So you might have C1, C2, etc. And at each one of those points I need to evaluate my function, in this case Q or A, at each of those numbers, my original function, not the derivative, and the largest value in the list over here will be the absolute max, and the smallest value will be the absolute min. Right. So we have to find critical numbers. To do that, I take the derivative, derivative of 6x is 6 minus 10x to the fourth. Right. It's clearly defined everywhere, but it's going to equal 0 whenever x to the fourth equals 6/10 or 3/5. So x will be plus or minus the fourth root of 3/5. Right. We don't care about minus here, right, because that would be outside of our domain, so we could ignore that. And this number is about 0.880. Right. Now, don't stop there. All I know is that I have a critical number at 0.880. I don't know if that critical number is a max or a min or neither. So somehow I have to make sure that I've answered the question, but I also have to justify that I've actually found the absolute maximum area. So to do that, we're going to use the closed interval method. I'm going to check at the ends of my interval. Okay. And I need to compute the original function at each point. Okay. What is my original function? Well, let's look at it as 2x times 3 minus x to the fourth. If I plug in 0, I obviously get 0. If I plug in 3 to the 1/4, this term is 0, so I get 0. So the absolute max is going to have to be here at 0.880. Right? And if I plug that in to my function for a, I get about 4.225. Now go back and read the question one more time. I know where the absolute max is. Have I answered the question? The question says find the maximum area. Well, we did that. So the absolute maximum area is 4.225, and we know when it occurs, though the question doesn't ask us for that.